Okay, so we're back to the setup of our benzene toluene distillation example problem. So far we have a basis, we've drawn our process flow diagram, and we've identified the what variables we ultimately want to solve for in this problem. Now, before we start applying material balances to try and figure out those variables, as I encouraged in the previous video, the next thing we're going to do is we're going to do a degree of freedom analysis to determine if we have enough information in our problem to solve for these unknown variables. All right, so degree of freedom analysis. And so for a molecular species material balance, which is what we're going to apply in this problem, the way we calculate the degrees of freedom is we first need to count up the number of unknowns. We need to add on the number of independent reactions. We need to subtract off the number of independent chemical species we have here. And then subtract off any number of other equations that we have that relate the variables. Okay? Alright, so based on our setup, we need to count up the number of each of these things that we have in this problem. So what I want you to do is I want you to pause the video here, and I want you to fill out this degree of freedom analysis and identify the number of each of these categories that we have. Okay, let's continue. So let's fill out our degree of freedom analysis sort of table that we have here. The first category we have is, what are the number of unknowns in our problem? And so if we go back to our process flow diagram, I've actually written all the unknowns in red, right? And so what we have is we don't know what M2T is. We also don't know what M3B is. And so the number of unknowns we have is 2, all right? So M2T and then M3B. All right, the next category is the number of independent reactions. And so in this problem, there is no reaction going on. All we're doing is we're separating the benzene from the toluene. And so in fact, our number of independent reactions is 0. The third category is the number of independent species in our system. And so the only species we have are the benzene and the toluene. And so that means our number of independent species is 2. So B and T. And the reason I'll point out that we count this up is because the number of independent species that we have in the problem is going to be equal to the number of different material balances that we could write for the problem. Okay? And so each material balance is another equation that we could use. All right, and then the final category is, what are some other pieces of information or other equations that we could use that relate, our knowns to our unknowns. And for this problem, we don't really have anything else, so that is going to be 0. Okay? And so now we could calculate our degrees of freedom for this problem. Okay? So in our case, it's just going to be number of unknowns minus number of independent species. And so what we have is 2 minus 2, and that gives us a value of 0. All right? And so this is an important result because this tells us we have enough info to solve for our unknowns. So now that we've determined that we have enough information, we can now move on to the next steps, which involve applying our actual material balances. So let's move on and start applying the material balances. So I'll move to a fresh page. And the first material balance I'll apply will be the one for the benzene in our system. And so All right, B, material balance. All right? And so anytime we start to apply material balance, we need to write the fundamental material balance equation. A equals I minus O plus G minus C, where A is accumulation, I is input, O is output, G is generation, and C is consumption. And so this is the full fundamental material balance equation. At this point, what we need to do is we need to start simplifying the system and canceling out terms that don't apply. Okay? And so what I want you to do now is I want you to think about each of the terms in this material balance equation and then figure out if we keep them or if we could cancel them out. Let's go through each of the terms one by one. So with the accumulation term, that's going to depend on if we have a steady state or unsteady state system. If we go back to our process flow diagram, all of our variables are given in terms of flow rates, right? Our units are mass per time. The way I set it up, I never said anything about these values changing over time, right? And so these values are steady over time, and so that implies that our system is at steady state, okay? And so if our system is at steady state, that means that our accumulation term is going to be equal to 0. All right? Let's now move on to the input and output terms. All right? So do we have input and output streams in our system? If we go back to the process flow diagram, our system is the distillation column, and we clearly have mass going into the system and also mass coming out of the system here. All right? And so for the benzene, that means we do keep our input and output streams. Now for the generation and consumption terms, once again, there's no reaction going on in this problem. So we could cancel those out. And so that leaves us with I minus O, output, is equal to 0. And we could rearrange it so that we just have our input is equal to our output. All right? And so there, we simplified our fundamental material balance equation into a relationship that says the amount of benzene that goes into the system must be equal to the amount of benzene that comes out of the system. All right? And so now let's identify what the input and output streams are. For the input stream, the only benzene that's coming into our system is in that feed stream, M1B. Okay? For the output stream, our benzene is present in both stream 2 and stream 3, plus M3B. All right? So now we could write out this relationship, M1B is equal to M2B plus M3B. All right? And in this equation that we just wrote, we know the value for M1B, we know the value for M2B, but we don't know the value for M3B. This is our only unknown. But this is good, because we have one unknown and one equation, right? And so that means we could just use a little bit of algebra to solve for M3B. Okay? So this is 500 kilograms per hour minus 450 kilograms per hour. And so that tells us that M3B is equal to 50 kilograms per hour. Right? And so anytime you have a final answer, you always need to box in your answer. So I'll emphasize it here. That must box in answers on homework, quiz, and exams. Okay. All right. And so we figured out what M3B is, one of our unknowns. We now need to figure out what M2T is, the amount of toluene in the top stream. All right. So I'll draw this dashed line to separate these sections out. All right. And so now let's apply our material balance for toluene. So once again, we need to write out the fundamental material balance equation. A equals I minus O plus G minus C. And at this point, what I want you to do is to pause the video and once again figure out what terms we could cancel out. Okay, let's go through each of the terms one by one. And so with the accumulation term, once again we could use the same argument we use for the benzene material balance, such that none of the streams in our system are changing over time. So that means we're at steady state. And if we're at steady state, that means that our accumulation term is going to be equal to 0. There's no reaction going on in this system, so generation and consumption are also going to be 0. And we do have toluene crossing our system boundaries. It's both going into and out of our system. And so the input and output streams are not going to be 0. And so what we're left with, once again, is that the input of toluene is going to be equal to the output of toluene in our system. For the input term, it's just going to be equal to the amount of toluene in the feed stream. And our output term is going to be equal to the amount of toluene in both the top and bottom product streams. So M2T plus M3T. We could write out this relationship by plugging in our variables. In this equation, we know what M1T is, and we also know what M3T is, but we don't know M2T. So just by performing some algebra, we could solve for M2T. So M2T is equal to M1T minus M3T, which is equal to 500 kilograms per hour minus 475 kilograms per hour. And that gives us 25 kilograms per hour of toluene in our top product stream. And so once again, it's necessary to box the answer. And so, by using both a degree of freedom analysis and material balances, we were able to identify the missing flow rates in our distillation column example problem.